Let's use statistical software and our toy data set to examine one-way analysis of variance. When we use statistical software, it's always a good idea to graph the different distributions of your data for each of these groups. A good way to do that is to use box plots. So here we have box plots for each of these different groups. So we have groups 1, 2, and 3. This is just using the same toy data set. And we can see that we have these different distributions. This just reflects the graphs that we saw earlier, where for group 1 we have values of 1, 2, 3, and 4. For group 2 we have values of 5, 6, 7, 8. And for group 3 we have values of 9, 10, 11, and 12. When we conduct our analysis using statistical software, we get the output shown here, where it says one-way analysis of means. We have an F test statistic of 38.4. You can see that is roughly the same within rounding of what we calculated by hand. You can see the output tells us we have degrees of freedom of 2 and degrees of freedom of 9. The statistical software says, it frames this in terms of the numerator denominator. That's because the F test statistic is based on the mean squares between divided by the mean squares within. Well, you could think of it alternatively as you have the numerator has a degrees of freedom, the mean squares between is based on degrees of freedom of 2, and the denominator has a degrees of freedom, which is based on degrees of freedom of 9. Using this F test statistic, the statistical software compares or places this F test statistic on the F distribution, governed by degrees of freedom of 2 and 9 respectively, and calculates a p-value almost at 0. This just reflects what we had just done earlier. Okay? So in this case, we would reject the null hypothesis. Now, we should also go back to our original example of the fat mice study. Recall that this is a study designed to compare different treatment control groups with the idea of asking the question, does light at night, does it increase weight gain? They're looking at mice, but they're really interested in people. So let's look at this data set again. Recall that we have these 3 treatment groups. Treatment and control groups. The control group is getting light during the day and dark at night, so that's what we'd expect with a normal cycle. But they have another group that has light all the time. They call LL, and they have another group that has sort of dim light at night, or DM. This is the set of results from statistical software. Looking at the box plot, you can see that these 3 different groups, there is some variability here. And then when we look at the one-way analysis of means, or variance, we get an F test statistic of close to 8. We have a degrees of freedom of 2 for our numerator. What that's referring to is the degrees of freedom related to the mean sum of squares. Right? That's because we have 3 groups, minus 1 equals 2. The degrees of freedom of the denominator is 24. That reflects the degrees of freedom corresponding with the sum of squares within. And based on the ratio of mean squares between divided by the mean squares of within, we get a p-value of 0.0017. That's less than our conventional standard of alpha of 0.05, so we reject the null hypothesis. We reject the null that the population means are the same, and we say that these groups really are quite different. In the context of this particular study, we can say these different exposure conditions, they do have different effects on the weight gain of mice. To put another way, these results suggest that being exposed to light at night increases weight gain in mice. Then the popular press picked this up and said, well, maybe you shouldn't be looking at your computer at night or watching television at night because that might increase weight gain. We can also graph this p-value and our F-test statistic. When we have a degrees of freedom of 2 and 24 respectively, the F distribution model looks like this roughly. The p-value is 0.002. That is just the probability of obtaining a test statistic as or more extreme than the one we obtained. The test statistic we obtained is about 8. The probability of obtaining a more extreme test statistic under the assumption that the null is true, under the assumption that the F ratio is 1, or equivalently, under the assumption that all the population means are the same, it's very unlikely that we obtain this data from random chance. So we can say that these group means really are quite different. These different groups probably do come from different populations.